Hello everyone, this is section 6.2, confidence intervals for the mean, typically when we have small samples. It's used when we don't know sigma, so sigma is not known, and either the population is normally distributed or n is greater than or equal to 30. So that's when we will use the t-distribution. There is a difference between when to use t and when to use z, and there's also a flow chart on that I posted on Blackboard, and this will be your cheat sheet for the final exam. You'll have an opportunity to write anything you want on the back of this document, and it gives you a flow chart. There's one in the textbook this is from an older textbook, but this one I think works well. You can look at the one in the new book if you like. But basically, it's based on do you know sigma. If you know sigma, typically it's going to be z, as long as the population is normally distributed or n is greater than 30, greater than or equal to 30. If you don't know sigma, then the population has to be normally distributed or n has to be greater than or equal to 30 as well. And then we're going to use t. And notice there's what we call degrees of freedom. So use that chart to determine z or t. And the properties of the normal distribution, well, it's similar to the z distribution in many ways. It's bell-shaped, symmetrical about the mean, but it's a family of curves. And it has what we call degrees of freedom, which are denoted by this formula, just simply n minus 1. Similar to z, the total area is 1 or 100%, mean, median, and mode are equal to 0, just like z. And as degrees of freedom increase, the t-distribution approaches the normal distribution. So a quick sketch to show that concept. If you have a small degrees of freedom, the t-distribution might be relatively flat, and the tails are thick. It's well above the x-axis, so that might be an example where the degrees of freedom are, let's say, 2, relatively small. But if the degrees of freedom increase to, let's say, 10, it starts to look a little bit more normal. But the tails are still kind of above the x-axis a little bit more than in the normal distribution. But as increases to be, let's say, 30 seems to be the magic number here, then it's going to look pretty normal. Okay, so the note mentions about the thicker tails, and then we have a table 5. Table 5 is in that same packet as table 4, and it's used to find the critical values for the t-distribution. Get familiar with the way the table looks. There's columns with confidence intervals, as well as in chapter 7 we'll be talking about one-tail and two-tail tests for hypotheses, but don't worry about that now. So you've got these columns with the respective confidence intervals. On the left, the degrees of freedom, and you intersect the row with the column, and that's your critical value. And there's a little sketch off to the side as well. And so here we'll just look at an example of finding the critical value for 95% confidence interval. So C is 95%, or 0.95. Tells us the sample size is 15, so n equals 15. We'll calculate the degrees of freedom. N minus 1, or 15 minus 1. Obviously, you don't formally need a formula for that. And then we go to table 5. So we have degrees of freedom of 14. And 95% confidence interval. So it's as simple as just looking under the 95% confidence interval, the third column here. Intersect that with the 14 degrees of freedom. And it looks like 2.145. So T sub C is 2.145. Alright, the nice thing about what we're going to do is, similar to the z distribution, we'll find a margin of error, but now with the distribution formula, where T is replaced by Z and sigma is replaced with S. And if you look at your formula sheet, it's got the confidence interval for the mean that would be using Z or T, and then it gives us our formulas for the margin of error for both for both Z and T. And again, just notice that Z sub C is replaced by T sub C and sigma is replaced by S. So make sure you understand the little table that I've written more than a few times. This is a helpful little table when talking about the population in terms of the notation, or a sample and their respective means and standard deviations. For a population, remember it's Greek letters, mu for mean, sigma for standard deviation, and for a sample mean we use X bar, and sample standard deviation we use S. So make sure when we get to word problems you're comfortable writing the correct symbol for the given parameter. Alright, here we want to find the margin of error for a 99% confidence interval given S and the sample size N. So C is 99%, or 0.99. To get the critical value, we need the degrees of freedom. N is 18, so degrees of freedom N minus 1. 18 minus 1, obviously 17. So then we go to table 5, and we look up the critical value for T. And it's probably the last time I'll show it because it's the simplest table we'll ever encounter, right? 0.99 confidence interval, our last column intersected with the row where the degrees of freedom are 17, looks like 2.898. So T sub C is 2.898, and then the margin of error. You don't have to write down the formula, but kind of nice to do so to get used to the notation and the symbols we use. Okay, so T sub C S over N, the square root of N. T sub C, just plug in 2.898 times S. Okay, that was given to be 4.4 here. Over the square root of N. And just make sure you put in N, not the degrees of freedom value. So 18 is N. And then you can check my computations. This is the same calculation that we did for Z in terms of the keystrokes. And we get 3.005. So on the next page we mention the confidence interval formula. As we know, subtract E from the sample mean X bar to get the left endpoint, add E to the sample mean X bar to get the right endpoint. We're trying to estimate mu, the population mean. There's the formula for E using the T distribution, again reiterated. So here it says for the situation in the last example, find the 99% confidence interval when the sample mean is 5.3. So again, sample mean X bar, 5.3. And so looks like we're ready to go because we already know E. That is from example 2. We know that the margin of error E was 3.005. So now for the confidence interval, X bar minus E is less than mu, which is less than X bar plus E. X bar was 5.3 minus the margin of error that we found to be 3.005. 0.005 is less than the population mean mu that we're trying to estimate, which is less than the sample mean, once again 5.3, and then plus the margin of error 3.005. So it looks like we get 2.295 is less than mu, which is less than the right endpoint 8.305. Or, as we've done in the past, if you like interval notation, left endpoint enclosed in parentheses, separated by a comma from the right endpoint, and close the parenthesis. Okay, so now they're just giving us everything, and we're going to put it all together. But we'll see word problems in a minute. But here they give us X bar, S, and N. Ask us to find the 95% confidence interval. So we could construct that. First, starting with the confidence interval, 95%, 0.95. The sample size was 22, so therefore the degrees of freedom, n minus 1, 22 minus 1, or 21. And we go to table 5. And to find the value of t sub c. And I'm going to assume you're comfortable doing that. So double check that, 2.080. And now construct the confidence interval. Okay, so the easiest way to go about it is first find E. So again, the formula t sub c s over the square root of n. So we get 2.080 is t sub c times s. Okay, that was given right here to be 0.5 over the square root of n. And again, make sure you use the n. It was 22. And check my computations to 3 decimals, 0.222. So now for the confidence interval, x bar minus e is less than mu, which is less than x bar plus e. So the sample mean x bar, that was a given 2 as well. It's 12.5 minus the margin of error, which is what we just found, 0.222 to give us the left endpoint. It's less than the population mean mu, which is less than the right endpoint, which is 12.5, the sample mean, plus that margin of error of 0.222. So we get 12.278 is less than mu, which is less than 12.722. Okay, so that's the mechanics. Now some word problems. So we randomly select 16 coffee shops, and we're measuring the temperature of the coffee sold. So right away we know n is 16. The mean temperature of the coffee sold at the 16 coffee shops is 162.0. So that would be the mean from these 16 coffee shops, which is a sample. So the sample mean, x bar, is 162.0. And the standard deviation of 10 degrees is coming from this sample of 16 coffee shops as well. So that's the sample standard deviation of 10.0. And so we associate S with that. So that's why it's extremely important to make sure you understand what symbol goes with the given information. And we'll worry about the 95% confidence interval in a minute, but the fact is that they're normally distributed. Okay, so if you're doing this on like the final exam or on the TOEFL, here. Okay, I think it's back. Okay, so we have, you tell us if it's C or T. And using the flow chart that we have, the first question is to determine if it's Z or T. Do we know sigma? And we don't know sigma, we know S, right? And so we don't know sigma, so we're over here. Is the population normally distributed? Yes, it is. Fortunately, because N is smaller than 30. So the more information, we could use the T. Okay, so using the T distribution, first we want to get the critical value. So it was a 95% confidence interval, so C is 0.95. The degrees of freedom are N minus 1, so 16 minus 1 or 15. And then we go to table 5 for the confidence, or for the critical T sub C critical value. And again, I'm going to trust that you're comfortable using the table, and we get 2.131. Okay, so now we're ready to do the computations. Here's the formula again. E is T sub C S over the square root of N, so we always find E first. So T sub C 2.131 in parentheses, that's the way I like to do it. That's times the standard deviation sample 10.0 over the square root of the sample size N was 16. So we get that E is equal to, I'm going to round it to 2 decimal places here, 5.33. Just pay attention to the rounding in my math lab. Okay, so now the confidence interval. So x bar minus E is less than mu, which is less than x bar plus E. And x bar, the sample mean, was 162.0 minus the margin of error of 5.33 will give us our left end point, which is less than the population mean, which we're trying to estimate, which is less than the right end point, which is the sample mean of 162.0 plus that margin of error of 5.33. So we get a left end point of 156.67 is less than mu, which is less than the right end point, 167.33. Okay, so a couple more examples to finish up this section. And the next one, another standard example, 10 randomly selected automobiles, so immediately we could say N is 10. Note the sample size is rather small, but that's typical of, you're not going to go out and, in this case, measure the tread depth of like 50 of them. 30 is a good number, but we can get away with smaller numbers, as we're seeing with this distribution. In any event, you measure the tread depth of the right front tire and the mean tread depth, and that's assuming it's coming from the sample of these 10 randomly selected automobiles. So sample mean, that would be x bar of 0.32, and the standard deviation is the sample standard deviation, so S is 0.08. We want 99% confidence intervals, but note that they're normally distributed. So again, using our flow chart, we don't know sigma, and so once again, you don't know sigma, So you look over here, and we have to have normally distributed, and we do, because n is not greater than or equal to 30, but that tells us we can use the t-distribution. So based on that data, we use the t-distribution. And so next thing to do is to find the critical value. Okay, it's based on a 99% confidence interval. C is 0.99 then. Degrees of freedom. I mean, just do it. It's 9, right? I mean, who's going to write n minus 1 or 10 minus 1 is 9? Not many people. But then we go to table 5. I mean, if you do, that's fine. I obviously do, just to make things clear. But now we go to table 5, and again, I'll trust that you can find the critical value from the t-distribution, and that is 3.250. Okay, so then we go to the formula for E. So T sub C, S over the square root of n, and plug everything in. T sub C, 3.250, multiplied by S, 0.08, divided by the square root of the sample size, n was 10. Okay, so all of the givens are on the right here. And so we calculate E, and double check my computations, 0.0822. So I'm going to 4 decimal places for some reason. And then the confidence interval. So x bar minus E is less than mu is less than x bar plus E. X bar sample mean is 0.32 minus the margin error we just found, 0.0822. Less than mu, which is less than the 0.32 plus the 0.0822. Alright, so left endpoint 0.2378 is less than mu, the population mean of these tread depths that we're trying to estimate, which is less than the right endpoint of 0.4022. Alright, so one final example, which is actually kind of a classic, because they don't give us the sample mean or the sample standard deviation, they just give us a list of the data. So we want to first find the sample mean, x bar, and then the sample standard deviation, and then construct the 90% confidence interval, and assume the variable's normally distributed again. So if we count up the values, there's 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. So n is 12. So now use the statistical features on your calculator. Okay, so you don't want to go through the formula by hand. That's just too tedious. So you want to use the statistical features on the calculator to calculate the mean and the standard deviation. So I've got a simple TI-30. If you don't know how to do this, email me. If you're using a graphing calculator, you could email me. And basically all I'm going to do is go on Google and say TI-83 sample standard deviation, and then you'll find a video on YouTube. In fact, you'll find many videos on YouTube that will tell you how to go about it. Using this TI-30, and again, just email me if you have concerns and you can't use it. We go to data. Oops. Gotta go into the stat mode first, so clear all that. Step variable. Go to the stat mode, which is above the data button. Oops, I'm going to turn it on first. Okay, and one variable statistics, so enter. And then my data, hit the data button. X1, 26. The way this works, it accommodates frequencies as well. So it's just a frequency of 1 we'll use for all of these. I'm not going to do it as a grouped frequency distribution or anything. So then I toggle down again. It tells me X2, 22. Hit the down arrow twice. 12. It's my third piece. 19. My fourth piece. 23. My fifth piece. Sixth piece is 14. 17. 24. 14, 23, 20, and finally 26. And notice how it's the 12th piece of data, right? Okay, so we'll leave that one blank and then go to second function data to get the statistics. One variable, press enter. I'm sorry, you hit stat variable, and then it brings up calculate, and you hit enter, and it does it for you. So there's n is 12, x bar is 20. So let's write that down, we need that. Sample mean is 20. Okay. That's what we want. We want S. Okay, we don't want the sigma. So on my calculator it shows sigma there. So we want S is 4.8. I'll use 4.824. Okay, so for when you're given this list of data, then use a calculator. If you have a graphing calculator, Google it or send me an email and I'll Google it for you and send you a link to a video. But once we have X bar and S, then we can continue to find, oh, and I should say here that it's normally distributed. And I should actually mention that that data tells us it's a T distribution again. Because using the flow chart, we don't know sigma, but it's normally distributed, so we're good to use T. Alright, so then the confidence interval was 90%, or 0.90. Degrees of freedom, n minus 1, 12 minus 1, or 11 in this case. So then we go to table 5, and we find that T sub C is 1.796. Okay, so now the standard calculations. E first, T sub C, S over the square root of n. Plugging in, T sub C was 1.796 times S was the 4.824 divided by the square root of n was 12. And so check my computations, 2.501. That's what I got free, so now the confidence interval. So left endpoint sample mean X bar minus E is less than what we're trying to estimate, the population mean, which is less than the right endpoint of X bar, the sample mean, plus E, the margin of error. And so plugging everything in, X bar was 20 from our computations that we made, minus E, the 2.501 is less than mu, which is less than 20, plus the 2.501. And so the confidence interval left end point 17.499 less than the population mean mu, which is less than the right end point of 22.01. Okay, so I get the end, but we're this, those, and little bottom tells you can find the flow chart. It's actually different from the one that I've been showing you because they created a new one, but I like the one I've been showing you. You can use either. Alright, so that's the end of section 6.2.